All right, today we are diving into something that sounds like science fiction but is very, very real. How in the world do you teach a computer to think with perfect, absolutely undeniable logic? I mean, really think about that. This is the big question, right? And we're not talking about AI in the way you might see in the movies. This is about building systems that can construct mathematical proofs with just absolute certainty. So where do you even start?
Well, first things first, you need a language. Just like musicians have sheet music to write down their ideas, and architects have blueprints, logicians need a formal way to write down arguments. And that brings us to a really elegant system designed for exactly that.
It's called natural deduction. And the really cool thing about it is that it's actually designed to follow the kind of intuitive steps our own minds take when we're working through a problem. It's logic that feels, well, it feels natural. But there are a few different ways you can actually write it down.
And this right here shows you exactly why one style is so popular. I mean, on the one hand, a proof can look like a total tangled mess. But then you have the Fitch style proof. Look how clean that is. It's organized, it uses simple indentations, it is easy to follow as a well-written recipe. It's fantastic for us humans. But that very clarity for us, well, that's what leads to our next big problem.
So we've got this great system that people can read and understand really easily. But that brings up the automation challenge. How do you get a machine to understand a system that's literally built for the human eye?
And that's really the heart of it, isn't it? A computer doesn't care about elegant visual layouts. It needs explicit, unbreakable rules. It's rigid. It's literal. So the whole game is about bridging that gap between our human intuition and cold, hard machine precision.
This is where we start opening up our toolkit. And the very first tool is all about transforming proofs, kind of reshaping them from one form into another.
We call it rewriting. And honestly, the best way to think about it is like a super powerful find and replace for logic. It's a way you can edit a proof to make it simpler or more efficient, all while guaranteeing it stays 100% logically correct. So here's how it works in practice. You start with a proof that, maybe takes the long way around. Then you apply a very specific rewrite rule, which is basically a proven logical shortcut. And what pops out the other side is a brand new proof that proves the exact same thing, but in a much more direct, much more efficient way. This is hugely powerful for stuff like program synthesis, where you're essentially building software straight from logical rules. Okay, so simplifying a proof that already exists is one thing. But how does a computer even find the proof in the first place? That brings us to our next set of tools. Smarter ways to search.
I want you to imagine that a proof is a journey. You're starting with your assumptions, and you need to get to your final conclusion. The problem is there could be millions, maybe billions of possible paths. How does a computer act like a GPS, avoiding all the dead ends and the wrong turns to find that one perfect route?
Well, it uses some pretty clever strategies. So instead of just guessing randomly from the start, it can actually start from the goal and work backward. It uses special techniques to make sure it never tries the same failed path twice, which saves a ton of time. And computer scientists have even designed these specialized rulebooks, they're called calculi, that are totally optimized for a machine to search with. These are the computer's detective methods for cracking the case.
But the most powerful tool in our box, the real secret weapon, it isn't a strategy at all. It's a discovery. It's like finding a secret code, a Rosetta Stone that connects two worlds we always thought were totally separate, the abstract world of logic proofs and the very concrete world of computer programs.
This is the Curry-Howard correspondence, and it is a total game changer. What it says is that for a certain kind of logic, any valid proof you can write has a direct one-to-one equivalent to a working computer program. And get this, any well-behaved program has a direct equivalent to a logical proof. Just let that sink in for a second. A proof is a program. A program is a proof. They are two sides of the exact same coin. This means the act of finding a proof is literally the same thing as the act of writing a program. This isn't just some clever thought experiment, it's a fundamental truth of computer science. Okay, so we've got these incredible tools, but how do we know they'll always work? How can we be sure the computer will find the best answer, or that it won't just get stuck and run forever? That's where the guarantees come in. Our first guarantee is something called cut elimination. Think of this as the promise of elegance and efficiency. It guarantees that if something is provable, then a clean proof exists,
one that takes the most direct route, like a nonstop flight, with no unnecessary steps or weird logical detours along the way.
And the second guarantee is normalization. This is the promise of completion. So while cut elimination guarantees a direct path exists, normalization guarantees that our process of simplifying and searching will actually finish. It ensures our proof editing process won't get stuck in some infinite loop. It will always arrive at that final, simplest possible form.
Okay, we have covered a lot of ground, so let's zoom out for a second and put all these pieces together to really see the bigger picture.
So here's how it all connects. We start with a format that's clear for us humans. That's Fitch style. Then we give the computer tools to work with, rewriting to make proofs efficient and smart search to find them fast. The real magic is the Curry-Howard correspondence, which connects this whole system to the world of actual software. And the whole thing is held together by proof theory, which gives us the guarantees that the process is sound and correct.
And here's the most important takeaway. This is not just some academic exercise for mathematicians. This is about building the future of technology. It's about laying a foundation for software that we can actually trust 100% because it's been mathematically proven to be correct.
So I'll just leave you with this question. What would our world look like if every critical piece of software, the stuff running our banks, our hospitals, our phones, wasn't just tested, but was mathematically proven to be perfect, to be bug-free? That is the incredible promise of automating logic.